Welcome! Today, we'll be tackling LeetCode problem number 885, titled Spiral Matrix 3. This problem challenges us to traverse a matrix in a spiral order while adhering to certain constraints. It's a great opportunity to practice matrix traversal techniques and refine your algorithmic thinking. Let's dive in and explore the solution approaches. In this problem, we are working with a grid that has R rows in C columns. You are given a starting position within the grid, denoted as rstart, cstart, and your goal is to visit every single cell in the grid exactly once. The twist is that the order of traversal must follow a spiral pattern. This spiral begins at the starting position, moving in a fixed sequence, first to the right, then downward, then to the left, then upward, and it keeps repeating this sequence as needed. If the movement takes you outside the grid's boundaries, that's okay, you continue in the same direction and re-enter the grid when it becomes possible. Ultimately, you need to return a list of all the cells visited, in the exact order that they are traversed during the spiral process. To better understand the problem, let's look at an example. Here, the grid has one row and 4 columns, and the starting position is 0, 0. As the spiral traversal begins, you first move to the right, visiting 0, 1, then 0, 2, and finally 0, 3. Since this grid consists of only one row, the entire traversal simply follows a straight line until all cells are visited. The output for this example is a list of the coordinates visited in order 0, 0, 0, 1, 0, 2, 0, 3. Now, let's consider a more complex example. Here, the grid has 5 rows and 6 columns, and the starting position is 1, 4. The spiral traversal begins by moving to the right, visiting 1, 5. Next, the traversal proceeds downward to 2, 5, then to the left, visiting 2, 4, and 2, 3. From there, it moves upward to 1, 3, and the pattern continues, expanding outward in a spiral until every cell in the grid is visited. The key here is that the traversal always follows the spiral pattern, even when it involves moving outside the grid temporarily. The final output is a list of all coordinates visited, in the specific order dictated by the spiral. In another example, we have a grid with 3 rows and 3 columns, and the starting position is 0, 0. The traversal begins by moving to the right, visiting the first row from left to right. Then it moves downward to visit the last column, followed by moving to the left along the bottom row. From there, the path moves upward along the first column and continues in this spiral pattern until all cells are visited. For this grid, the output reflects the order of traversal 0, 0, 0, 1, 0, 2, 1, 2, 2, 2, 2, 1, 2, 0, 1, 0, 1, 1. This example highlights how the spiral adapts to different grid dimensions while ensuring every cell is covered. Finally, it's important to consider some edge cases. For instance, if the grid has only a single row or a single column, the spiral traversal will naturally reduce to a linear path that visits all the cells in sequence. Similarly, if the starting position is close to the grid's boundary, the traversal may initially move outside of the grid before re-entering to continue the spiral. Regardless of the grid's dimensions or the starting position, the output must include every cell in the grid exactly once, maintaining the spiral order as defined. To approach the spiral matrix 3 problem, one straightforward method is the brute force approach, where we manually iterate through all cells in the grid while simulating a spiral pattern. The idea is to maintain a visited array to keep track of the cells we've already covered. Starting from the given position, rstart, cstart, we use nested loops to move in a spiral direction right, down, left, and then up while ensuring we stay within the grid bounds. For every valid cell, meaning it falls within the grid dimensions and hasn't already been visited, we append it to our result. While this approach is intuitive and easy to implement, it's not the most efficient. The repeated checks for grid bounds and the visited status can introduce unnecessary computational overhead, and the algorithm also requires additional space to store the visited array. Overall, while functional, this method has some clear trade-offs in terms of efficiency and redundancy. An optimized strategy for solving this problem is the directional simulation approach, where we eliminate the need for a visited array by simulating the spiral outward in incremental steps. The core idea here is to use a predefined sequence of directions right, down, left, and up represented as coordinate changes 0, 1, 1, 0, 0, -1, and -1, 0. Starting from rstart, cstart, we initialize a step size and proceed by moving in the current direction 4 step iterations before turning to the next direction in the sequence. Each time we move, we check if the current cell is within the grid bounds, and if it is, we add it to the result. This process continues until we've appended all our *C cells. The main advantage of this method is that it avoids the overhead of maintaining a visited array, while still efficiently covering all cells in the grid. However, it requires careful management of both the step size and the direction changes to ensure accuracy. Overall, this approach simplifies the movement logic and reduces unnecessary computations, making it more efficient than the brute force method. Ultimately, the optimized spiral algorithm stands out as the chosen strategy for this problem because of several key insights. First, the incremental outward expansion of the spiral naturally avoids the need for a visited array, significantly simplifying the implementation. Second, by using predefined direction changes, the movement logic becomes more streamlined and less error-prone. Additionally, the grid bounds check ensures that only valid cells are appended, maintaining the correctness of the result. A crucial realization here is that spiral traversal follows a geometric pattern, and alternating step sizes allow us to navigate this pattern effectively while avoiding redundant checks. This approach is efficient, traversing all cells in *C time, and it avoids extra space usage, making it highly scalable for larger grids. While managing step sizes and direction changes adds a bit of complexity to the implementation, the trade-off is worth it for the cleaner and more efficient solution. This strategy balances performance, simplicity, and robustness, making it the optimal choice for Spiral Matrix 3. To solve the Spiral Matrix 3 problem, we need to simulate a spiral traversal starting from a given cell and expanding outward. The challenge is to visit all cells in a grid while maintaining the correct traversal order. The first step is to initialize the necessary variables. We create a result list to store the order of visited cells. To control the spiral movement, we define the 4 possible directions, right, down, left, and up, represented as coordinate offsets. We also need to keep track of our current direction using a direction index, starting with dir equals 0, which corresponds to moving right. Additionally, we set the starting position, r/c, to the given rstart, cstart, coordinates. Now, to handle the spiral growth, we introduce 2 counters, steps, which determines how many cells to move in the current direction, and step counter, which tracks how many steps have been taken so far. Finally, we use a change step flag to manage when to increase the step count, ensuring that the spiral expands outward evenly after every 2 direction changes. The next part involves simulating the spiral traversal. We continue the process until we have visited all the cells in the grid, which is checked by the condition len, result, rows * calls. First, we move in the current direction. If the current cell, R/C, lies within the grid boundaries, we add it to the result list. Then, we increment step counter to track the steps taken in this direction and update the position, R/C, based on the current movement direction. Once the required number of steps for the current direction is completed, indicated by step counter equals steps, it's time to change direction. We reset step counter to 0 and adjust the direction index using modular arithmetic dir equals dir plus 1, %4, cycling through right, down, left, and up. If the change step flag is true, we increment the steps counter by 1 to expand the spiral outward. Afterward, we toggle the change step flag to ensure the step increment happens only after every 2 direction changes. When all cells are visited, the result list, containing the traversal order, is returned. There are a few key insights that make this algorithm efficient and robust. First, the spiral expansion alternates between maintaining the same step count and increasing it by 1, ensuring the traversal grows symmetrically outward. This systematic growth guarantees that all cells are eventually visited. Another critical aspect is bounds checking. Before adding a cell to the result list, we verify that the cell lies within the grid's valid coordinates. This prevents accessing invalid positions. Additionally, the use of modular arithmetic for managing direction changes keeps the implementation clean and eliminates the need for repetitive condition checks. The algorithm relies on simple data structures to achieve this. The result list stores the final sequence of visited cells, while the direction array simplifies the movement logic by predefining direction offsets. Finally, the counter's steps and step counter ensure precise control over the traversal, enabling accurate spiral expansion at each step. Analyzing the algorithm's complexity, the time complexity is O(n), where n is the total number of cells in the grid. Each cell is visited exactly once, making the traversal linear with respect to the grid size. The space complexity is also O(n), as the result list stores all visited cells. Several edge cases need to be considered to ensure correctness. For example, if the starting position, rstart, cstart, is outside the grid boundaries, the algorithm should handle it gracefully. Grids with only one row or one column, or small grids like 1 by 1 or 2 by 2, require special attention because the traversal completes quickly. On the other hand, large grids demand efficient handling of numerous direction changes as the spiral expands. Addressing these edge cases ensures the algorithm is robust and performs well across all possible inputs. This solution simulates the traversal of a grid in a spiral order. Starting at the given cell, rstart, cstart, we proceed in a spiral pattern until all cells in the grid are visited. Explanation of the code asterisk. 1. Initialization. The result list will store the order of visited cells. We define directions to represent the movement directions: right, down, left, up. The steps variable starts at 1 and determines how many steps we take in the current direction. The direction underscore index keeps track of the current direction. 2. Starting point. The starting cell, rstart, cstart, is added to the result list initially. 3. Spiral traversal. The while loop continues until all rows asterisk calls cells are visited. For each step size, we repeat movement in 2 consecutive directions, e.g., right and down for step size 1, left and up for step size 2, and so on. For each step in the current direction, we update the row, R, and column, C, by adding the respective direction offsets from directions. If the new cell, R, C, is within the grid boundaries, it's added to result. For direction updates, after completing a direction, the direction underscore index is increment, modulo 4, to cycle through the directions. After 2 directions, the step's value is increment. 5. Termination. The loop terminates once all cells in the grid have been visited. The final result list is returned. This approach ensures that we visit all cells in the correct spiral order while maintaining efficient boundary checks. The time complexity is O, rows asterisk calls, since we visit each cell exactly once. Here, we're implementing the spiral matrix 3 problem in Java. First, we declare the method spiral matrix II, which takes the number of rows and columns in the matrix, as well as the starting row and column. We initialize a result array to store the coordinates of the spiral traversal, with its size equal to the total number of cells in the matrix. Next, we define a directions array to represent the 4 possible movement directions: right, down, left, and up. The variable steps is used to track the number of steps we need to take in the current direction, starting at 1. The starting coordinates are stored in R and C, and direction index is initialized to 0, indicating the first direction, which is right. We also initialize index to 0, which keeps track of our position in the result array. The first coordinate, which is the starting cell, is added to the result array. To traverse the matrix, we use a while loop that continues until we've visited all the cells. Inside the loop, a for loop runs twice for each step size, ensuring that we move in pairs of directions, such as right and down, or left and up. In the inner loop, we adjust the coordinates based on the current direction, and if the new cell lies within the matrix bounds, we add it to the result array. After completing one direction, we update the direction index to the next direction in a circular manner, using modulo arithmetic. Once we've processed 2 directions for the current step size, we increment the steps variable, which ensures that we expand the traversal outward in a spiral pattern. The process continues until we've filled the result array with all the coordinates of the spiral traversal. Finally, the result array is returned, containing the spiral order of all the cells in the matrix. This implementation ensures that we handle edge cases, such as starting near the boundary or at the corners, and works efficiently for matrices of any size. To solve the spiral matrix 3 problem, we start by looking at example 1. Here, the grid has dimensions of 1 row and 4 columns, and the starting position is at the top left corner, 0, 0. We initialize our directional movements as right, down, left, and up, represented as 0, 1, 1, 0, 0, -1, -1, 0. Initially, we set the steps to 1, and our result array contains just the starting position, 0, 0. Now, we begin the process. Starting at 0, 0, we include it in the result. Moving in the first direction, right, we take one step and arrive at 0, 1, which is valid, so we include it in the result. Next, we attempt to move down by one step to 1, 1, but this position is out of bounds, so we skip it. At this point, we increase our step size to 2. Moving to the left for 2 steps, we pass through both 0, 0, and 0, minus 1, but only 0, 2 is valid within the grid, so it is added to the result. Then, moving up for 2 steps takes us to minus 1, 2, and minus 2, 2, both of which are out of bounds, so we skip them. This process continues until we have collected all 4 positions in the grid. The final output for example 1 is 0, 0, 0, 1, 0, 2, 0, 3. Now, moving to example 2, the grid dimensions are 3 rows and 3 columns, and the starting position is at the center, 1, 1. The directions remain the same, right, down, left, and up, and we initialize the steps to 1. The result array initially contains just the starting position, 1, 1. From here, we begin the traversal process. Starting at position 1, 1, we add it to the result. Moving in the first direction, right, we take one step to 1, 2, which is valid and added to the result. Next, moving down by one step, we reach 2, 2, which is also valid and added to the result. At this point, we increase our step size to 2. Moving left for 2 steps, we pass through 2, 1, and 2, 0, both of which are valid and added to the result. Then, moving up for 2 steps, we pass through 1, 0, and 0, 0, and both are added to the result. The step size is then increased to 3, and the process continues, expanding outward in a spiral pattern. We repeat this process until the result array contains all 9 positions in the grid. In example 3, we now have a grid with 5 rows and 6 columns, and the starting position is 2, 3. Once again, our directions are right, down, left, and up, and we initialize the steps to 1. The result initially contains just the starting position, 2, 3, starting from 2, 3, we add it to the result and proceed in the first direction, right, moving one step to 2, 4, which is valid and added to the result. Next, moving down by one step, we reach 3, 4, and this is also added to the result. We then increase the step size to 2 and move left for 2 steps to 3, 3, and 3, 2, both of which are valid and added to the result. Moving up for 2 steps, we pass through 2, 2, and 1, 2, adding both to the result. The step size is then increased to 3, and the process continues outward in a spiral pattern, ensuring that every valid position is added to the result until it contains 30 positions. The final output for example 3 is a complete list of all 30 positions traversed in spiral order: 2, 3, 2, 4, 3, 4, 3, 3, 3, 2, 2, 2, 1, 2, 1, 3, 1, 4, 0, 4, 0, 3, 0, 2, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 3, 5, 2, 5, 1, 5, 0, 5, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0. This demonstrates how the algorithm systematically covers all positions in a grid of any size, expanding outward in a spiral pattern and adapting to the grid's boundaries as needed. The time complexity of this solution is O, rows asterisk calls. To understand why, let's break it down. The algorithm generates the coordinates for a spiral traversal within a grid of dimensions rows x calls. First, it iterates over the steps and directions, incrementing the step count after every 2 directions. Since we need to visit all the cells in the grid, the total number of valid coordinates to be processed is exactly rows asterisk calls. For each movement, the algorithm checks if the current cell lies within the grid's boundaries, ensuring that only valid coordinates are appended to the result list. This while loop continues until all grid cells have been visited, and since each coordinate is processed exactly once, the time complexity becomes proportional to the total number of cells, which is O, rows asterisk calls. To further solidify this, we can look at a proof of the big O complexity. The outer while loop runs until all rows asterisk calls cells have been added to the result list. As for the inner loops, while the step sizes increase over time, the total number of movements remains proportional to the grid size because we are only processing valid cells. Thus, the total amount of work done by the algorithm corresponds directly to the number of grid cells, giving us O, rows asterisk cols, time complexity. Now, regarding space complexity, the solution also requires O, rows asterisk cols. This is primarily due to the result list, which stores all valid coordinates in spiral order. The memory used by auxiliary variables, such as the current position, direction index, and step counts, is constant and doesn't depend on the grid size, contributing only O1 to the space complexity. Therefore, the dominant factor is the result list, leading to an overall space complexity of O, rows asterisk cols. When comparing this approach to more naive methods, we see why the given solution is efficient. A brute force approach might involve nested loops traversing the grid, with additional manual handling of direction changes. While this would also result in a time complexity of O, rows asterisk cols, it could be less efficient due to redundant computations or repetitive boundary checks. In contrast, the optimized approach minimizes unnecessary operations. By directly calculating the next coordinates based on step size and direction, it avoids redundant checks for invalid cells and ensures only the valid ones are appended to the result list. Whether in the best, average, or worst case scenarios, the time and space complexity remain O, rows asterisk cols, as all grid cells are always visited and stored in every instance. To summarize, the time complexity of this solution is O, rows asterisk cols, because each valid cell is visited exactly once. The space complexity is also O, rows asterisk cols, due to the need to store all valid coordinates in the result list. This makes the solution both time and space efficient for generating the spiral traversal of a grid. By optimizing computations and avoiding unnecessary checks, the algorithm achieves the best possible complexity for this problem and ensures consistent performance regardless of grid size or shape. One common mistake in spiral traversal problems is not handling edge cases like empty grids or grids with only one row or column. These scenarios often lead to runtime errors if not accounted for. To prevent this, always check if the number of rows or columns is 0 before proceeding. Another frequent issue is incorrectly updating the boundaries for the spiral traversal. The top, bottom, left, and right bounds need to be adjusted only after completing a full pass in the current direction. Missing or misplacing these updates can result in infinite loops. Additionally, overcomplicating the tracking of visited cells is another pitfall. Instead of using a separate visited array, you can often modify the input matrix directly by marking visited cells with a special value, reducing both space usage and complexity. Another mistake to watch out for is incorrectly setting the termination condition for the spiral traversal. If you rely solely on boundary checks, you might stop too early or continue too long. The best approach is to use a counter to track the total number of visited cells and terminate when this count equals the total number of cells in the grid. Inefficient approaches can also be problematic, especially those with time complexity of O(n) squared or worse. For example, brute force solutions that repeatedly check visited cells or perform redundant operations significantly slow down the traversal. To ensure efficiency, focus on clear boundary updates and avoid revisiting cells, aiming for an O(m*(n) solution. Spiral traversal problems often revolve around simulating directional movement, making it crucial to recognize common patterns. At its core, spiral traversal involves moving in a sequence of directions right, down, left, and up, while shrinking the boundaries after each full pass. This insight simplifies the problem and helps with related tasks like matrix rotation or boundary-based traversal. When explaining your approach in an interview, emphasize how you handle edge cases and maintain constant time updates to the bounds. A clear explanation of how you track state, including direction and visited cells, is key. For test cases, be prepared to discuss scenarios like an empty grid, single row or single column grids, square matrices, and rectangular grids. These examples demonstrate a thorough understanding of edge cases and robustness in your solution. Spiral traversal concepts appear in several related problems, making it valuable to recognize these connections. For example, problem 54, spiral matrix, is a classic example of traversing a 2D grid in a spiral order. Problem 59, spiral matrix 2, involves generating a spiral matrix filled with sequential numbers, which builds on similar logic. Problem 48, rotate image, requires rotating a matrix clockwise, which shares similarities with spiral movement. Another related problem is problem 73, set matrix zeros, which involves careful grid traversal and in-place modification, echoing the challenges seen in spiral traversal tasks. These related problems highlight the versatility of mastering spiral traversal techniques. One effective approach to solving spiral traversal problems is iterative simulation, which is both simple and efficient. This method involves defining boundaries for the top, bottom, left, and right edges of the grid. Using a while loop, you traverse in the four directions right, down, left, and up, shrinking the boundaries after completing each full pass. The traversal stops when all elements have been visited. This approach achieves O(m*n) time complexity and uses only O(1) extra space. Alternatively, recursive simulation processes one layer of the spiral at a time. A helper function handles the current layer, and the recursion continues into the smaller, inner submatrix. While this method is easier to visualize, it requires additional space proportional to the depth of recursion, which is O(m*n). Another approach is to use a visited array, where you maintain a separate matrix to track which cells have already been traversed. During the traversal, you check both the grid boundaries and the visited status of cells before proceeding. While this method ensures correctness, it comes with significant trade-offs. The additional visited array consumes O(m*n) space, and the overall approach is less efficient compared to boundary-based solutions. This makes it less ideal for scenarios where space efficiency is critical, but it can be a helpful fallback for clarity during initial problem-solving stages. Great job today! To summarize, we explored the problem of spiral matrix traversal, discussed a brute force approach, and highlighted the importance of handling grid boundaries effectively. Be sure to practice more grid-based problems to solidify your understanding. Thank you for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!